Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at a topic in A-level mathematics, the remainder theorem. So let's see what the remainder theorem is. It says that given a polynomial in the variable x, if we divide the polynomial by x minus a, then the remainder can simply be worked out as substituting a into the polynomial. So let's look at an example. Let's say our polynomial is x squared minus 4x plus 5. So we're going to divide this by x minus 3 by polynomial division. We looked at this in a previous video. I'll put a link in the description. So we can see that when we carry out this long division, we get a remainder of 2. Long division takes a while. Should we just go back and do the long division? Let's do this first one. So dividing x minus 3 into x squared minus 4x plus 5. So how many x's in x squared? The answer is x. That way we've got an x on the top. Then we do x times x minus 3 gives us x squared minus 3x. We take that away from x squared minus 4x gives us minus x. That is correct. Bring down the plus 5. How many x's in minus x? Well, there's minus 1, so you get minus 1 on the top. Minus 1 times x minus 3 is minus x plus 3. So we take minus x plus 3 from minus x plus 5 and we get a remainder of 2. Whereas if we just say, well, look, px is x squared minus 4x plus 5, that's the original polynomial. We put 3 in, we get 3 squared, which is 9, minus 4 times 3, which is 12, plus 5 just gives us a straight 2. Let's look at a cubic. So x cubed minus 3x squared plus 3x plus 3. We're going to divide by x minus 1. When we do that, when we go right through the process, so how many x's in x cubed? Well, there's x squared. X squared times x minus 1 gives us x cubed minus x squared. We've got minus 2x squared left over. So on and so on. We just follow the process through, and in the end we get remainder 4. But what we could have done is put 1 into the cubic. So we're dividing by x minus 1. So 1 is playing the role of a in our remainder theorem. So essentially, to get the remainder when you divide by x minus 1, all you need to do is just substitute in 1. So polynomial of 1 is 1 minus 3 plus 3 plus 3, which is 4. Here's one where we've got no x term, so this is just x squared minus 5 as the polynomial. So when we do the division here, we say how many x's in x squared? Well, the answer is x. X times x minus 3 gives us x squared minus 3x. Subtract them, you get plus 3x. Take down the minus 5. How many x's in 3x? Well, it's just plus 3. And then 3 times x minus 3 is 3x minus 9. Subtract them and you get plus 4. The remainder theorem just allows us to do it. You just put in the 3 for x, so you get 9 minus 5 is 4. Here's another one. X minus 3 into x squared minus 4x plus 3. Now when we follow this through, we find remainder 0. And we ask ourselves, well, is there something special going on? And there is, and we'll look at that in the next video. This is linked to the factor theorem, which is if the remainder is 0, then x minus a, in this case x minus 3, is a factor. And we can actually see that x squared minus 4x plus 3 equals x minus 3 times x minus 1. The remainder is 0, x minus 3 is a factor. So we'll look at the factor theorem in the next video. We can also work out the remainder this way. So px equals x squared minus 4x plus 3. We're dividing by x minus 3, so we substitute in 3. 3 squared is 9, minus 4 times 3 is minus 12, plus 3. 9 minus 12 is minus 3, plus 3 is 0. So we did a video on proof earlier on. I'll put the link to that in the description too. We did a video on proof. So how do we prove the remainder theorem? How do we know that it's true? Because in mathematics, we need to know that things are true. So firstly, we can say, well, every polynomial px can be written as px can be written as a quotient qx times x minus a plus a constant remainder r. So then when we put in a, x minus a goes to 0, so we end up with q of a times 0 plus r. So q of a times 0 is just 0, so you just get left with r, the remainder. That's kind of how it works. But actually, that's the proof, but maybe we need a proof of the proof. Because what we need to establish is, how do we know that every polynomial can be written as q of x times x minus a plus r? Well, the way we do it, let's take an example to show how this works. So let's say p of x is x squared minus 4x plus 5. The first thing is we get rid of the x squareds, and we do that by taking off the number of x minus 3's we need to get rid of the x squared. So if we take off x times x minus 3, then basically that's like taking off x squared minus 3x. So if we take that all away from the left-hand side, we just get left with minus x plus 5. Then we want to get rid of the x's out of minus x plus 5. So we're just taking off minus 1 version of x minus 3. So we take that off. So now we can write the right-hand side as x minus 1 times x minus 3, because we took off x minus 3's. Now we're taking off another 1 x minus 3. Or actually, we're taking off another minus 1 lots of x minus 3. And so we're left with plus 2 on the right-hand side. So x squared minus 4x plus 5 equals x minus 1. So in this case, x minus 1 is the q. X minus 3 is playing the role of x minus a, and then plus 2 is the constant remainder. And basically we can see that in each case we can take off enough versions of x minus a to leave us just with a constant remainder. And actually what this is just doing polynomial long division in a slightly different way. We're doing polynomial long division, but we're sort of doing it in our heads. And this allows us to prove that every polynomial px can be written as qx times x minus a so-called linear factor, plus a constant remainder r. I really hope you like this video. If you do, please drop a like, as they say on YouTube. You're very welcome to subscribe. We're going to send more videos in the future, and hit the notification bell if you want to see the videos. I'd love to hear your ideas, and I very much hope you enjoy your mathematics.